Hello and welcome back. My name is Mike Price. Today we're going to be talking about section 1.3 from the text, lines and linear functions. This first video we're going to talk about this first learning objective, review properties of lines, slope, horizontal and vertical lines, and forms of the equation of a line. So the most interesting, definitive characteristic about a line is this idea of slope, which is constant for any point on a line. That's kind of its most, its claim to fame, if you will. So slope between 2 points, any 2 points, is this equation you've probably seen before a few times. So it doesn't really matter in what order we take these to begin with, as long as A, we're subtracting y values on top. So always the second coordinate, the height of these points. And then on bottom, we're always subtracting the horizontal component, the x values. And then B, the second thing that we have to keep track of is that whatever order we pick, we do them in the same on top and bottom. So if you notice, x2 and y2 come from the same point, and x1 and y1 come from the same point. So as long as they're sort of aligned this way, where we do the subtraction in the same order on top as we do on bottom, we're going to get the same correct slope. So a line is a special graph for which the slope is always the same. It's constant. So no matter which 2 points you pick, x1, y1, and x2, y2, you'll always get the exact same slope on a line. And it turns out that we get an equation that models this, which looks something like this. You've probably seen y equals mx plus b a million times in your experience. Funny little fact, it seems odd that we would call m, which is the slope of this function, it seems weird that we would use m to represent something that's slope. It doesn't seem like there's m in there anywhere. Maybe s would be more obvious. So it turns out there's no great agreement about why this is the case, but one possible explanation is something like, it turns out that English-speaking mathematicians aren't the sole contributors to math. I mean, right, go figure. So one supposition is that this is M from the French for to climb, and you'll pardon my butchery of the lovely language, but monter. So if M is for monter, then you'd think, okay, to climb is like a slope. So maybe that's where that M comes from. Yeah, as far as B is concerned, I got nothing. It's probably just second letter there. No special things. But B, we'll see, has also a great interpretation as the y-intercept. So the upshot is a line can be written in this form, which is convenient for us. Y equals mx plus b. So one quick example. So this certainly defines a line. We've got the slope, evident right there. It's a constant, and it's multiplied by x. We've got another constant being subtracted or added. You could think of it as adding -3. And so this line has slope of slope of 3/4. And then if we were to graph that, here's our line, courtesy of Wolfram Alpha. And basically the thing we should keep track of here, if we want to verify slope, is that this is, in some sense, rise over run, if you will. So if we start from any point, but maybe here's a good one to begin with, and we go up 3 units, in order to get a new point on the graph, we have to go over 4 units. So that's the slope, rise, vertical component, and run, horizontal component. The -3, as you can see, has also a useful interpretation here, and that is it's the y-intercept. And there's nothing special that we need to prove that. If x was 0, then that whole first term there with the 3/4 x would be out of the mix. If x was 0, this whole term would be gone. So when x is 0, y is equal to -3. That's exactly what it means to be a y-intercept. At x equals 0, you have a point on the graph at -3. So finding the equation of a line. So if we're given a couple of points, as we are in this case, -1 comma 4 and -5 comma -8, we're supposed to find the line that contains these. And again, of course, because a line has constant slope throughout, all we need is 2 points to define a line. Equation of a line can be written as y equals mx plus b, so we need to know what these two constants are. As soon as we know the value of m and b, we've got ourselves a line. So first things first, we could find the slope between these points using the slope formula. I've chosen to use -1 and 4 as the x1 and y1, you could think, okay, that's because they come first, but it turns out it doesn't actually matter at all. But the thing to keep track of in this case is that 4 and -1 came from this first point, and -8 and -5 came from this second point. It's probably worth underlining that in green too. Huh? There we go. Color-coded. So as long as we keep the ordering the same between these points, we should be in business. All right, and you'll notice that the y values are on top, -8 and 4. The x values are on bottom, -5 and -1 respectively. And then as long as we do our subtraction responsibly here, -1 is actually +1. -5 minus -1 is -4 on the bottom. -8 minus 4 more is -12 for a grand total of slope 3. And here's kind of the state of the union, if you will. We've got y equals 3x plus b, and that's great. We figured out what m is, but we're still missing out on this second constant. So we need to know what b is, and it doesn't actually matter how we go about this, except that the one remaining piece of information we have not yet employed is that we've got a couple of points on this graph. So really, at this point, actually, we're doing nothing special except knowing that we have a point on the graph and that there's one constant we have left to find. So what we're making use of is the fact that if we know an x and a y combination, that is a point, then we can use this equation to solve for b. And that's exactly what we're going to do. So I think it's worth pointing out or mentioning again that we did not need to use -1, 4. We could have used this other one, -5, -8, right here. But if you got to pick between 2 points and either of them will work, you might as well pick the one that's nicer. And I think of not having negatives as being equivalent to nicer. So I use -1, 4. That means that the x value gets plugged in right about here. The y value goes in where y is. And you'll notice this is the nice equation with b is the only thing that we don't know. We add 3 to both sides and blam, we got b equals 7. So great, there's the equation of our line. I want to step out for a moment just to talk about horizontal and vertical. So these are two special cases for lines. So the y equals mx plus b thing is great, and in fact, you might notice, this does not preclude the use of our y equals mx plus b equation. If you want a horizontal line, the thing that most, wow, I actually made a horizontal line, look at that, that's like the first time ever. The first thing that we could think of characterizing a horizontal line is that it's flat, and you could think of this as having slope equal to 0. The rise is 0, and because there's no up and down, but there is any amount of run that you might want. So this is equivalent to thinking of y equals 0 x plus, and if you'll allow me the creative moment to say we don't call it b, but we call it c. That's just the constant on the end. So if we have 0x, certainly we didn't need to write all that stuff. We could have just written y equals c. So this is actually not a new definition. This is just considering a slope with a line with slope 0. Vertical line is kind of a different creature. We have to consider a function, we have to consider an equation that has basically undefined slope. I'm not getting my hopes up too great that I can draw a vertical line here, but that's pretty close. So unfortunately, our y equals mx plus b situation doesn't really pan out here, because this has no run, but it has rise. So if we had a number with some y distance on top, but no x distance on bottom, that's a problem. If you recall, division by 0 is undefined, so the slope is undefined. That means that I can't really write y equals mx plus b here because there is no slope. And I don't just mean 0 slope. That would be fine. There is a slope I cannot define. So what is consistent about this, though, is that up and down, we stay constant at a horizontal value. So we pick some horizontal value to be at, and it's always true that that's the case. That's what it means for y equals x equals c to be the equation of our line. You always have this x value. Y could be anything you want, but you always have this x value. So just a couple of graphs to throw out there. Graphs of lines y equals 2, so this fellow right here, and then and then x equals -1 would be So again, what's consistent about y equals 2 is that it is at a constant height of 2. What's consistent about x equals -1 is that it is a constant horizontal component of -1. It never varies to the left or to the right at all, but you can go up and down as much as you want. Great, that's it for Learning Objective 1 and 1.3. I'll see you again for the next video.